Section 47 is entitled Change of Variables. The Jacobian method, using Jacobians. So first, let's learn how to find a Jacobian. In fact, let's define it. Jacobians are normally written like this. And this has no meaning until I define it. It's a determinant. It's a partial of x with respect to u, partial of x with respect to v, then the partials of y with respect to u and v. It's the determinant. That is, it's this product minus this product. So let's compute a Jacobian. Suppose x is negative a half u minus v, and I meant to write y. Y is equal to, say, a half u plus v. That is, it's negative a half u plus a half v. A half u plus a half v. So, for shorthand, I'll call it J for Jacobian. What's the Jacobian? Well, it's the partial of x with respect to u. Then, the same x, but now with respect to v, is a half. Second row is partials with respect to y. So partial of y with respect to u, partial of y with respect to v. You multiply those two numbers, whatever you get, you take away from that what you get when you multiply those two numbers, which they're meant to write negative a quarter minus a quarter, which is negative a half. Took away 2 quarters, which means you took away a half. And that's the Jacobian. Try one more, and then we'll make a change of variables. This is like the U substitutions back in Calc 1. You took a somewhat complicated integral, you made it into an easier one. Suppose x is equal to u cosine theta minus v sine theta, and y is u sine theta plus v cosine theta. What's the Jacobian? Well, it's a determinant. The first row, first is the partial of x with respect to u, which will just be cosine theta. Partial of x with respect to v, which will be negative sine theta. Remember, cosine theta and sine theta are constants in terms of u and v. Partial of y with respect to u. U times the constant. Derivative is the constant. Here's a function of v. Partial of y with respect to v would be cosine theta. This product is cosine squared theta minus, this product is negative sine squared theta. You can change both of those signs and then say, oh, I recognize that identity as 1. Cosine squared theta plus sine squared theta is 1. So that Jacobian is 1. Okay. Now, let's learn how to change from xy coordinates, or xy plane, to the uv plane. Suppose you have the xy plane, and it contains these 3 points. The origin, which is 0, 0, the point 2, 3, and the point 3, 0. And you're given the translation. You're told that x is 3u plus 2v, and that y is 3v. And your goal is to convert the xy points to uv points. You want to write 0, 0 in the xy plane as some uv in their uv plane. Same with 2, 3, and the same with 3, 0. Well, for example, I could immediately find y, or v, excuse me. If I divide both sides by 3, I get v is y over 3. So I take I take v divided by 3. That's v. I take y divided by 3, that's v. I take y, I divide it by 3, I now have v. Okay. Now, updating this equation, we know that v is y over 3. Now, I hate having fractions, so I multiply everything by 3. When I multiply this by 3, I get 3x. When I multiply this by 3, I get 9u. And the reason I'm multiplying by 3 is to kill off that 3. So I get plus 2y. This equation I can solve for for u. I can solve for u. First I'll solve for 9u. Let me bring this to the other side. So 3x minus 2y equals 9u. Divide by 9, and now I have a way of getting u's. Triple x, double y, subtract. Divide by 9, you get u. If I triple x, I get 0. If I double y, I get 0. If I subtract, I get 0. Divide by 9 is 0. If I double x, triple x, excuse me, I get 6. And if I double y, I get 6. And I subtract and divide by 9. 0 divided by 9 is 0. I triple x, I double y, and I subtract and divide by 9. That's going to give me 1. So I have the ability right now to draw the UV plane. It contains 0, 0, 1, 0, and 0, 1. And you just connect the dots, just like we did in the XY plane. We took 0, 0, 2, 3, 3, 0, and we connected the dots. So that's the new region that we are integrating over. But we just wanted to make the change of variables. I drew the new region and I changed, I found the new points and I solved for v in terms of x and y and u in terms of x and y. Here is what I'm really looking for. That's the change of variables. That's the change of variables. So suppose you were given this. You want to evaluate this double integral. You want to evaluate this where x is 1/2 u plus v and y is 1/2 u minus v. By making the change of variables. So this is the double integral. 48 is 48. Let's find out what xy is. X times y is x. The sx times y. The order you multiply is up to you. I want to do a half times a half, quarter, and take that answer, multiply it by u plus v times u minus v. Multiply by what that is, which is u squared minus v squared. Okay, and I left out a dy, excuse me, dy. And xy is 1/4 times u squared minus v squared. Now dx dy, it becomes the absolute value of the determinant, of the Jacobian times du dv. So now we have to find the Jacobian. In fact, I want the absolute value of the Jacobian. It's the determinant, but determinants can be negative. Take the absolute value of it. It's the first row, the partial. Let's expand this. Okay, if you can do it without expanding it, good. Up here. 1/2 u plus 1/2 v. So it's the partial of x with respect to u, which is a half, and with respect to v is also a half. The partial of y with respect to u is a half, and with respect to v is negative a half. So this becomes this product, which is negative a quarter, minus that product, which is a quarter, the absolute value of that. But we just did that problem. It's negative a half, the absolute value is plus a half. So we have the Jacobian. It's a half. It is 1/2. Okay, 2 times 4 is 8, which will go into the 48 12 times. No, 6 times. 8 goes into 12. 8 goes into 48 6 times. And the 6 I'll factor in front. The 1s are meaningless. So what survived is u squared minus v squared du dv. Now, in addition to giving us this right here, in addition to that, they gave us the region to integrate over in the xy plane. They gave us the region that they wanted us to integrate over. They wanted us to integrate over this region. 0, 0, 1, 1, 2, 0, negative 1, 1. They want us to integrate over that region. And of course, this is in the xy plane. Now, coming here, if you add x and y, you just get u, because the these cancel out. If you do x minus y, you'll get v. Okay, well that makes life easy. Add x and y, get u. Subtract x and y, get v. The points we have are 0, 0, 1, 1, 2, 0, negative 1, 1. First number is x, second number is y. To get u, to get the u value, add x and y. 0 plus 0 is 0, 1 plus 1, 2 plus 0, negative 1 plus 0. 1, 2, 3. I'm not going to spend 10 minutes on doing that. It amazes me how long and tedious an instructor can make this. X plus y. V is x minus y. That x minus that y. 0 minus 0, 1 minus 1, 2 minus 0 is 2. 2 minus 0 is 2. And negative 1 minus 1 is negative 2. So the points that we have are 0, 0, 2, 0, 2, 2, and I don't know why we're not getting 0, 2. I defined x correctly. I defined y correctly. Okay, obvious reason. This point down here, negative 1, 1, that's wrong. X is 1. Y is negative 1. It's 1, negative 1. And then when we do x, take away y, we do get 2. We get 2. Which are these 4 points? 2 and 2. That means u goes from 0 to 2, and v also goes from 0 to 2. The double integral. U goes first, it goes from 0 to 2, and then v takes over and goes from 0 to 2. Now, this integral in front of us is not a bad integral. We went from one that, in my opinion, if I'm not mistaken, wasn't that hard, to something that's hard. Excuse me, something that's easy. When I say it wasn't that hard, I'm wrong. It's a little bit hard. It's a little bit hard because on this interval, from top to bottom, you have the equation of this line and the equation of that line. That is, y goes from this equation to that equation. But to the left of this to the right of this imaginary line, that changes. That changes. The lower limit is now a different function. The upper limit is now a different function. So you had to breaking it up to sums. That's a little difficult. I won't say it was smooth sailing, but to be honest, it's probably easier than doing the Jacobian. But on the exam, you're going to be asked to make a Jacobian substitution, and you want it to be a simple integral. Okay, nonetheless, the 6 is in front. First, we're going to do the first integral, which is with respect to u, with respect to u. The integral of u squared is u cubed over 3, and the integral of v squared du will just be v squared u. And u goes from 0 to 2. You plug 2 in, you get 8/3. You plug 2 in, you get v squared times 2 minus, which is the same as 2v squared. And you integrate this from 0 to 2 with respect to v. So you get 8/3 v minus 2v cubed over 3 from 0 to 2. You plug in 2, you get 16/3 minus 2 cubed is 8 times another 2, 16/3, which is 0. The area was 0. Actually, the volume was 0. So, the question here is, what do you do if you're not given the u and the v? Well, I just want to point out one other thing. If you have an integral say like this, x plus y raised to the x minus y dy dx. And they tell you that x is 1/2 u plus v and y is 1/2 u minus v. If you add the two, that tells you x plus y is u. If you subtract the two, x minus y is v. So this would become, x plus y would become u, and this x minus y would become v. So, and dy dx becomes absolute value of the Jacobian du dx, du dv. All I'm saying is that this function of x and y, you have to write down in terms of u and v. Well, actually, we did that in the last problem. We had to compute x times y. So in this problem, we just want to set up the integral. Use the change of variables to find the volume, or to find an integral that will calculate the volume of a solid region lying between the surfaces z equals here's one similar to the one we just had. It lies between this and it lies below z and above the plane region R, the region R. And the region R is defined to be these four corner points of a square or rectangle. These four corner points of a quadrilateral. I really should be saying that, because right now my region is just 4 points. But I'm saying it's the quadrilateral with those 4 corner points. 4, 0, 2, 2, 6, 2, 6, 2, and 4, 4. 4, 4. So this quadrilateral. That's all they tell you. So basically, they want you to find the double integral over the region x plus y e to the x minus y dx dy. They want you to find that volume, or to set up an integral to find that volume using u's and v's. That is to make the substitution change. Well, find the equation of each of these 4 lines. I notice by inspection that when I add the x's and the y's, I get 8. Do you find anything true about 2 points on a line? You have the equation of the line. I notice if I compute x minus y, I get 4. 6 minus 2 is 4. 4 minus 0 is 4. Over here, I notice that x plus y's add up to 4. It's not because I'm brilliant. It's not because I'm smart. It's because I look. I look. People don't teach you to look. I look here and I say, oh, how nice. The y's and x's are the same. Which, by the way, can be written as x minus y equals 0. Okay. I have x plus y, x plus y. how about we let u equal x plus y? Not because we've done that in the past, but because it came up. X minus y, x minus y. Let v equal x minus y. Adding these two together tells me that 2x is u plus v, but I'll divide by 2. And if I do u minus v, I get 2y. Well, I don't want 2y, I want 1y, so I'll divide by 2. Okay, we'll use that in a little bit. Now, I want to find the new points. I want to find the uv points. So xy, uv. In xy, we have 4, 0, 6, 2, 2, 2, and 4, 4. To get u, you add x and y. 4 plus 0, 6 plus 2, 2 plus 2, 4 plus 4. To get v, we do x minus y. 4 minus 0, 6 minus 2, 2 minus 2, 4 minus 4. There are my 4 points. 1, 2, 3. The u, v axis. U likes to hang out at 4 and 8, and v 2 and 4. So here's 4, 4, and here's 8, 2, and 4, 0, and 8, 0. Six, 2, 4, 4, and 2, 0. You add the x and y's, and you subtract. Okay? X minus y. 6 minus 2 is 4. So it wasn't 8, 2, but rather 8, 4. And it's a nice square. So what I know is this becomes the integral of x plus y, that's u. X minus y is v, so it's e to the v. The absolute value of the Jacobian, which we haven't even touched yet, times du dv. dx dy becomes the Jacobian, or the absolute value of the Jacobian, times du times dv. And u goes between 4 and 8, and so 2 never really came up, not that it matters. And y goes between, I meant to say v goes between 0 and 4. Alright. So before we can even attempt to find this integral, we need to find their Jacobian. And we are going to use the x equal and the y equals formula. So their Jacobian is the partial of x with respect to u, which is a half. Same thing for partial x, partial u. But when it comes to v, I meant to say y, the partial of u with respect to u will be 1/2, but the partial of v, the partial with respect to v will be -1/2. So once again, we have -1/4, -1/4, we have -1/2. So the Jacobian, the absolute value, is 1/2. It is 1/2. And this is an integral that a double integral that you can easily solve. And it became an easy one. Okay, and if you don't think it's easy, and think about how hard the original one was. Okay, that finishes this section.